In this video, we will cover nonparametric tests of significance. Specifically, we're going to discuss the two-way chi-square test along with the median test. There are two tests in your textbook that we will not be covering in class, the Mann-Whitney U test and the Kruskal-Wallis test. Please feel free to examine these tests if you like, but they will not be part of our quiz, practice assignment, or exam 2. Nonparametric tests of significance can be used for data at any level of measurement. However, they're generally used when we have nominal or ordinal data. And for this video, I will use an example of the median test because in the course of performing a median test, we can actually calculate a two-way chi-square as well. I will use a question from your textbook which reads, two samples of students were asked to read and then evaluate a short story written by a new author. One half of the students were told that the author was a woman, and the other half were told that the author was a man. The observations were obtained, higher scores, meaning more favorable evaluations. So I've got the scores for the two groups right here. The scores on X1 are evaluations for when the author was thought to be a woman, and X2 are observations when the author was thought to be a man. And so for this data, we could also perform a t-test, as it appears to be more or less interval level data. In the case of the t-test, our research hypothesis would be that the population mean evaluations differ between the two groups. So we're looking at the means when we're talking about a t-test. For a median test, our research hypothesis is that the population medians differ between the two groups. And therefore, our null hypothesis that we will evaluate with our chi-square test is that the population medians are identical. The first step in performing a median test is to determine the overall median of the data. So I'm going to copy all of the individual scores for each group into one long column so I can find its median. So I will select all of the scores in X sub 1. I'll copy them and I'll paste them in the all group. And I'll do the same for the second group. Copy them and paste those scores below. Next, I'll label each of the scores so it's easier to locate the median position once we get to that point. I'm going to start with 1, 2, 3. Then I'm going to select these and drag it down. And as you can see, we have 32 total scores. That's the magic of Excel. We can make a quick numbering of all of our scores that way. And the next step is to sort our data. And to do this, I'm going to highlight the whole column of all of the scores. I'm going to go to the Data tab above. I'm going to click on Sort. And it's going to ask me if I want to expand the selection or continue with the current selection. I want to continue with the current selection. Press Sort. And then it gives me some other options. One of the things it asks me is if my data has headers. And if I said yes, then it would not include the first observation there. So I have to unclick that. And then I want my data to go from largest to smallest. So I'm going to click OK. So now you can see that the data is completely in order just the way we need it for finding out the median. So next I want to find out the median position. And before I do that, I'm going to put 32. That is our number. And if you remember from an earlier video, the median position is equal to n plus 1 divided by 2. So what I'm going to do is I'll fill in that formula. We've got our n of 32 plus 1. Now I'm going to divide this addition term by 2, so I'm going to have to put this in parentheses so that it doesn't divide the 1 over the 2. Okay, let's see, why is that not working? There we go. Over and divided by 2. Okay, so our median position for this set of scores is going to be 16.5, which means that the median is somewhere between, or it's exactly between the 16th and the 17th score. So I'm going to go down to our median position here, and we have our 16th and 17th score here, and the answer is going to be 5 is going to be our median. So I'm going to place the median right there. Now, you remember that we actually could have just found the median by selecting all the scores and using the median function. Let's try that. MDN. And I'm going to do equals. I'm going to click on the, do I still have the median? I do right there. And I'm going to use the control button to select the first group of scores, and then as well as the second group of scores. Hit return. And that gave us the same median there of 5. So 5 is going to be our median for the calculations that we're going to be doing in the chi-square. And our next step is to create a table that shows how many observations in each group are above or below the median. I say below or at because when we have a score that is actually at the median, it's going to be in this bottom, the bottom cells. So is it above the median or below or at the median? So another quick way to do this is I'm going to sort each individual row to get the scores in order. I'm going to hit the data, sort, continue with the current selection, sort. My data does not have headers. I would like to go largest to smallest. All right. And so now what I'm going to do is I'm going to do a count for group 1 of how many are above the median. So I'm going to do equal sign, count. You could just count these two, but I like to be fancy. And I'm going to select everything that's more than 5, which is these numbers here. So we have 4 scores in group 1 that were above the median. I'm going to do the same for below the median for group 1. So it's going to be the median of 5 and everything below. All right. And so we have 12 scores in group 1 that were below the median. So I need to sort this group first, don't I? Let's see. Select them. Go to sort. Continue. No header. Largest to smallest. I'm going to find all of the scores now that are above. Oops, I need to count them though, don't I? That's what I'm doing. Count the scores that are above 5. Okay. And now I'm going to count the scores that are 5 or below, the median or below. Okay. So now we have 9 scores in the second group that are above the median and 7 scores that are below the median. And at this point, we have a cross tabulation of numbers based on 2 variables. And so now I'm ready to perform a chi-square test. Chi-square tests require that we know the marginal totals. And so I'm going to total each row and column right now. Equals, this time sum. Select the 2 cells. Oh my, I did something. Try that again. Equals sum of these 2 cells. Alrighty, there we go. Oops, I don't need to do that. I can just drag this over. Okay, and then I'm going to do equal sum and pull these 2 cells and drag that down, not just to the next cell, but the very next cell following it too. And so we can see that our marginal totals have added up correctly. 4 plus 9 is 13, 12 plus 9 is 7 is 19, and then when we add these numbers together, we get this grand total of 32. And so now we have our marginal totals, which is something that we need. And now we're ready to perform our chi-square test. Here is the formula for chi-square. It's going to equal the sum of the observed frequency minus the expected frequency squared for each cell over the expected frequency. So that might seem a little abstract right now, but I've created a table that will help us to walk through each step. The formula only requires 2 variables, our observed frequencies and our expected frequencies. And the observed frequencies, we should just add those in right here. So A1 is 4, A2 is 9, A3 is, or B1 is 12, and B2 is 7. And so now we have, these are the observed frequencies, the frequencies that we see in our data. The expected frequency can be found by clicking on the equal sign, and the formula for the expected frequency is first we're going to multiply for the A1 cell, which is right here. We're going to multiply the A marginal, the above marginal, times the net marginal for group 1, and close the parenthesis, over the total. And so this is looking at cell 1, or cell A1 actually, and taking each of its marginals and multiplying them, and then dividing it by the total. And we end up with 6.50. I'm going to do that without talking for the rest of them, and you can follow along. Okay, so now we have expected frequencies for each group based on the marginal totals. And so for cell A1, the expected frequency, with all things being equal, is that there should be 6.5 people in that group, and 6.5 people should be in A2, 9.5 in A1, and 9.5 in A2. So we have our expected frequencies. And the next thing that we're going to do is we're going to subtract our expected frequencies from our observed frequencies. So here we go. Equals. Okay, I can just drag this down once I've got the formula in. And I'm going to back up for just one moment. On your expected frequencies, they should sum to, what do you think? What do you think they're going to sum to? They sum to your n. So your expected frequencies are going to be equal to this total n. Your deviation frequencies, this is a deviation score essentially, what should that equal to? You know. 0. So your deviations, like any other deviation scores, are going to equal to 0. All right, so far our check of our work tells us we've done everything right so far. The next thing I'm going to do is take the observed frequency minus the expected frequency and square it. Simple enough, right? Whoops, if I select the right key. All right, so, and I'm going to drag that down. And that gives us an interesting, all the same for that term. And then finally, we're going to take at the end the squared deviation that we just found, and we're going to divide it by the expected frequency for this cell, which is in this case 6.5. And I'm going to drag down the rest. So now we have that column populated. And the last thing that we're going to do for our chi-square statistic is to add these up. And I just added it up. We get a chi-square observed of 3.24. And just with other tests of significance, once we calculate our statistic, we can compare it to a critical value for this statistic, given our degrees of freedom. So we don't have our degrees of freedom yet, so let's do that. The formula for degrees of freedom for a chi-square median test is simply the number of rows in our table, minus 1, times the number of columns in our table, minus 1. And so you'll notice that our table has 2 rows and 2 columns, so let's plug in that formula here for the degrees of freedom. Equals, I'm going to put the first subtraction term in parentheses. We have 2 rows minus 1, put a multiplication sign, and we have 2 columns minus 1. Okay, and you know what this is going to be. Our degrees of freedom are going to be 1. And so I'm going to pull up the chi-square table, the critical values of chi-square at the 0.05 and 0.01 levels of significance. In my book, it's table F, but I think most of you have an earlier edition and it might be labeled something different. For 1 degree of freedom, our critical chi-square value at 0.05 is 3.841. So let's put that in. 3.841. Okay, so our observed chi-square statistic is less than the critical chi-square statistic, and so we're going to go ahead and retain the null because we have not found a significant difference. We have not found a chi-square that exceeds, oh my goodness, I don't want to do this, a chi-square that exceeds 3.84, so we're going to retain the null. Well, that was not too hard, but I am wondering if any of you caught the fact that I've done this chi-square test incorrectly. Did you catch it? Well, this is the formula for a chi-square, but there are certain instances in which you want to add a correction to the formula. The correction specifically applies to 2x2 tables which have fewer than 10 observations in any given cell, and you will notice that 3 out of our 4 cells meet that criterion. And so we need to apply a correction called the Yates correction. And if you're following along with the practice Excel sheet, go down to the bottom and click right here where it says Yates, and that's going to bring us to a next page. Here's the formula for the Yates correction for chi-square. And what Yates basically does is discounts each deviation by 0.05 before we square it. And this ensures that our chi-squares are not unreasonably inflated by low observed frequencies. Since we want the size of a deviation to be 0.5 smaller regardless of its sign, we have to incorporate what is called an absolute value as well, and I'll walk you through that. So here's a table that I've constructed to include the steps needed to perform a Yates correction on our data. Our observed and expected frequencies are the same, and therefore our deviation scores are going to be the same. That hasn't changed. But the first thing we have to do after calculating the deviation score is to take its absolute value, which means we get rid of any negative signs. You can easily do this by hand, but I'm going to show you the Excel function for doing it. You press equals, and I think I still have the ABS symbol there. I'm going to select the number in the previous cell and press return. And so what you can see very clearly is it got rid of the negative sign here. So it got rid of negatives, making it an absolute value. And so now instead of negative 2.5 and positive, they're all positive 2.5. Now, before we square these numbers, we have to then make this Yates correction, and that is subtracting 0.5 from each of these numbers. So I'm going to do that right now. So there we go. And of course, it's going to be 2. Probably do that in your head. Oh no. Okay, hold on for a sec. There you go. And now we can proceed along, and it's going to be very similar to the last test, which is equals to the adjusted number squared. Easy enough. Pull that down. And now we're going to take the adjusted number squared and divide it by the expected frequency. There we go. Divided by the expected frequency, and that gives us 0.62. And I'm going to drag these puppies down, populate everything, and our last step then is to sum it up. And we end up with a new chi-square statistic of 2.07. And notice that this is smaller than a calculated chi-square from our previous example, and that is the point of the Yates correction. It produces a more conservative test statistic. Since our larger chi-square did not meet the criteria at the 0.05 level of significance, clearly our new lower calculated chi-square does not either. And so our decision is still to retain the null hypothesis that there is no difference in evaluations based on the sex of the author. So I hope this made sense to you. I think it's kind of fun. I like chi-square. Your practice assignment for this week has 4 items. One is a one-way chi-square, which we didn't compute in this video, but is very simple and is laid out well in your textbook. You're going to do another problem, which is a chi-square with Yates correction, just like we've just done. You're going to do another chi-square without a Yates correction, and then finally a median test that we did originally with a Yates correction. And as you work through these problems, please bring questions to the discussion board.